Hello, so today I'm looking at M3 International A-Level January 2015. This is question 4. So I have a light elastic string which has natural length 5 and modulus 20. So I'll just make a note of that. The natural length is 5, modulus 20. The ends of the string are attached to two fixed points A and B which are 6 meters apart. So I can see that it's stretched by 1 meter originally, on a horizontal ceiling. A particle P is attached to the midpoint of the string and hangs in equilibrium at a point which is 4 meters below AB. Calculate the weight of P. So the very first thing that I'll do is draw a diagram. So okay, so I have A and B here, and then I have 4 meters below, so it looks something like this. Okay, because they said the particle is attached to the midpoint, so I know that the particle is here now. And this distance is 6, so what I might do is just draw this in. So I know that's 3 and that's 3. And I know that this distance will be half of the natural length of the whole thing plus an extension. So when you have this kind of example where the particle is attached to the midpoint of the string, then it's a good idea to actually kind of consider this to be two strings where the natural length is each is half of this amount. So here I know that this is 2.5 plus the extension, as is this. They told me that this distance here is 4, and I can see here that I've actually got the 3, 4, 5 triangle. So that means that 5 is this length, 2.5 plus x, so therefore the extension is 2.5. Okay, so then they wanted the weight of P. So if I draw a separate diagram to show what the forces that are acting on P are. So here I have P, I have the weight, which is what I'm looking for, and then I'll have a tension here and an equal tension here. And I know that from Hooke's law that the formula for the tension is lambda times the extension over the natural length. So I'm doing 20 times by the extension divided by the natural length, which in this case is going to be 2.5. So let's just tidy this up. I know that 2.5 goes into 10 4 times, so into 20 will go 8 times, so basically I get 8x here. So here I have 8x, and here I have 8x, and I just need to figure out what this angle is here. So let's call this theta. This angle corresponds to this angle here, and I can see that tan theta is 3/4, which would mean that cos theta would be 4/5. Okay, so now using resolving upwards, this is in equilibrium, so I know the forces up equal the forces down, so basically I'll have 2 times this tension times by cos theta will be equal to the weight, and so the weight will be 2 times 8 is 16 times 2.5, which was the extension, so that's 5/2, multiplied with cos theta, which was 4/5. Okay, so I can see that this will cancel with this will cancel with this and give me a 2, so I end up with 16 times 2, which gives me 32 newtons. So that is part A. Looking at part B, it says there's some extra information here. The particle is now raised to the midpoint of AB, so that's here, and released from rest calculate the speed of P when it has fallen 4 meters. So basically, when the particle is on the level with AB, then we have kinetic energy 0, elastic potential energy. Was it stretched when it was at AB? Well, yes it was, because the natural length of this was of each part of this is 2.5 and 2.5, so there is a small extension in each of the parts, so there is some elastic potential energy here, and also there's some gravitational potential energy when it's at the top. Okay, when it reaches 4 meters lower than this, so 4 meters, it says calculate the speed, so there is some speed, therefore there is some kinetic energy. If we look at the elastic potential energy, we know that there is some, and we know what that extension is when it's down there. And then if we take there to be no gravitational potential energy when it's at the bottom here, so I'll do conservation of energy. So the elastic potential energy and the gravitational potential energy at the top will be equal to the kinetic energy and the elastic potential energy at the bottom. So at the top I have the elastic potential energy will be so lambda, which was 20, over so lambda over 2L, so 2 times the natural length. So when it's like this, I can just consider, when it's up here, I can just consider it as one piece of string with the natural length of 5. So here I'll do 20 over 2 times 5, which is 10, times by the extension squared, and the extension at that point is 1, because it's 6 take away 5. The gravitational potential energy is mgh. Now mg is the weight, so 32 times the height, 4. The kinetic energy when it's at the bottom, well, this time I have lambda over 2L, so this time I'm considering it as 2 strings where each of them has a natural length of 2.5 and each of them has this extension of 2.5 as well. So 2 times 2.5 is 5, multiplied by the extension squared, which is 2.5, so that's 5 over 2 squared. Now that's the extension in 1/2 of the string, so then I just need to multiply that by 2, and then I've got the kinetic energy, which is half mv squared. So I've got half, the mass will be the weight divided by g times v squared. So now I need to tidy this up and rearrange it to get v. So if I just what the most efficient thing to do would be is to type in this minus this, and then multiply by 2g and divide by 32, and then square root. But I'll just work out each of these terms so that you can see exactly what numbers you should be getting for each of the parts. So here I've got 20 divided by 10, which is 2, times 1, so I've got 2. 32 times 4 is 128. Here I've got 20 over 5, which is 4. Okay, so I've got 4 times brackets 5 over 2 squared times 2. And so here I end up with 50, and here I end up with 16 over g v squared. So I get 2 plus 128 minus 50 times by 9.8 divided by 16, and then square rooted, so I end up with v is the square root of 49, which is 7 meters per second. Okay, so that part of the question is worth 5 marks. The first part was worth 6 marks, so altogether you have 11 marks overall. I hope you found that solution helpful. Do click like if you liked it, and good luck with your studies.